Okay, here's some additional examples on related rates, things that we went over in class, and I thought I'd upload some additional examples for you all. Important topic, fun topic. So as we read this, we have two cars starting from the same point. So here's the starting point. One car travels south at the rate of 60 miles per hour. The other car travels west at the rate of 25 miles per hour. So one car is traveling south at a particular rate, 60 miles per hour. Another car is traveling west at the rate of 25 miles per hour. Okay. Now the question is going to be, at what rate is the distance between the two cars increasing? So what I have here is a picture of the situation. They're asking at what rate is the distance between the two cars increasing 2 hours later. So this is going to be a time value, 2 hours. Now, the instructions here for related rates questions are always to draw a picture of the question and determine the related rates equation for the geometry of the situation. Identify the known variables and the unknown variables. And so, since this is using, to some degree, navigational language, north, south, east, and west, it's not formal navigational language, but we still need to know about north, south, east, and west. So you have two cars that are moving. They started in the same position. So I'm going to let the variable x be essentially the distance that car 1 is traveling, since it's going south. So that's going down. And that variable is changing. So x is changing. They gave us a rate for that first car. So if I let x be that distance, this rate is 60 miles per hour. This is what they gave me. And that's the orange portion. We also know another car that was traveling west at that rate. The y variable is that distance. And the change in y over the change in time is 25 miles per hour. So this was given to us as well. So this is the given information, the variables that are changing. And then the question is, at what rate is the distance between the two cars increasing? So we let z be the distance between the two cars here, because after 2 hours, I guess, yes, time is 2 hours. So after 2 hours, we have car 1, car 2, and the distance between the cars is z, and that sure enough is increasing. So this is dz dt, and we don't know what that is. Now notice they're positive. So these rates that they gave us were positive because they're increasing. 60, 25, and then that z value will be increasing. It's going to be positive as well. So we kind of know what to expect. So this is the geometry that I'm referring to for this particular example. And then you might say, well, what do we know about these variables, x, y, and z, and geometry? Well, this is a right triangle. So by nature of this question, traveling due south and traveling due west creates a right angle here, so it's a right triangle. So by Pythagorean theorem, we know that z squared will be x squared plus y squared. That's what we know about this particular geometry. Now, remember, they say draw a picture of the question. That's essentially what you see there. Determine the related rates equation after we find the variables. And that's what you want to do now, determine that related rates equation. So differentiate both sides with respect to t. Now remember, these variables are changing over time. So they're all functions of t. So z is a function of t, x is a function of t, y is a function of t. They're functions of time. So that when you differentiate here, you get 2z dz dt. This is by chain rule. On the right side, the derivative of a sum is sum of derivatives. So if you want to just go back, and we can do this all together, not a big deal. But what I want to make sure we know is that every variable x, y, and z is changing. There is no constant values here for these variables. So that when you differentiate using the power rule with chain rule, make sure you include the chain portion. Okay, this is the chain portion right here, dt. So in red, by chain rule, dz dt, dx dt, and dy dt. And you can see also that your 2's, if you divide both sides by 2's, they cancel. And so we get a related rates equation. dz dt, x, dx dt, y, dy dt. Here's that related rates equation. And that's what we want to notate here. So all of these variables are changing, x, y, and z. And that should make sense because, you know, you have cars starting to travel and they're moving at that constant rate, 60 miles per hour. That first car going south, the next car going west, 25 miles per hour. All these variables, x, y, and z, they're changing. And so they want to know, here's the question now, 2 hours later. So here's the thing, if we go back to the related rates equation, we have dx dt given to us. That value is 60. dy dt is 25, and they're miles per hour. They want to know what dz dt is. And so if you look back at this, you say, wait a minute, I need a z value, I need an x value, and I need a y value. Now these variables, z, x, and y, apply really to the right triangle. See if I can draw one. There we go. They apply to this right triangle 2 hours later. And they're not rates, they're distances. Z, x, and y represent a distance. Now, you might say, I'm going to make this a bit longer. Let's try to see if that's a right triangle. Okay. So the question is, what is x, y, and z? Well, we know something here. The x variable is traveling at 60 miles per hour for 2 hours. So remember that distance is rate times time. So for the x variable, that's 60 times 2. So the x variable will be 120 2 hours later. The y variable, 25 miles per hour times 2. So the y variable is actually going to be 50 miles per hour. So we're going to use this information. The x variable is 120. The y variable is 50. So we have the x variable, 120. The y variable is 50. This is that x variable. This is the y, and that's distance. The question is, what is z now? Now, since this is a right triangle, we can very easily get z, the z variable, by Pythagorean theorem. This is what we know. So by Pythagorean theorem, Z squared is 50 squared plus 120 squared. And Z will be plus or minus square root of 50 squared plus the square root of 120. Z is positive. 50 squared plus 120 squared. So Z is going to be approximately, let's get our TI calculator out. And so I'm going to go to the TI here. Let me find this button. All right, TI, here we go. And I'm going to say, no, we want to go to the TI. Okay. Strictly the TI. There we go. Second square root, 50 squared plus 120 squared. And we're going to get 130. So this is the value for Z. So Z is 130. So I'm going to get rid of that. There's my Z. And so you might say, do I plug in Z being 130, X being 120, Y being 50? And the answer is yes. All right. So let's do some more algebra. 130 dz dt equals 120 times 60 plus 50 times 25. So dz dt, if I divide both sides by 130, this is what we'll get. Okay. TI. 120 times 60 plus 50 times 25. Close that. Divided by your 130. And this is the rate of change of that Z variable. 65 miles per hour. There we go. And that's what they wanted to know in this particular example 6. So, what is the distance between the two cars increasing? It's a rate. What is the rate here? Change in Z variable over time, because that's changing as well, that variable. It's getting bigger. So, ladies and gentlemen, a pretty good question. Love that question. So I thought I'd share it with you guys. So, the rate in which the distance between the two cars is changing is 65 miles per hour. Related rates. There we go. Now, here's another question that's a little bit more complicated than the first. It's still a navigational type of situation. It's still describing motion. So we're going to go read and see what we can figure out here. And they're saying at noon, ship A. This is a ship question, not a car question now. Ship A is 150 kilometers west of ship B. So the distance between these two ships at noon is described to be 150 kilometers away. Okay. Now they're saying ship A is sailing east at 35 kilometers per hour. So for ship A, I'm going to call this dA dt because this is a rate. And that's 35 kilometers per hour. Okay. Ship B is sailing north now. So dB dt at 25 kilometers per hour. So this is another rate. Okay, so notice what's going on here. How fast is the distance between the two ships changing at 4 p.m.? In other words, 4 hours later. T equals 4 hours. So how fast is the distance between the two ships changing here? Okay, so how fast is the distance between the two ships changing? Now remember, like the last example, we want to draw a picture of the geometry. So here's what we're going to have to relate here, okay? Here's the hint. Draw a picture of the question and determine the related rates equation for the geometry of the situation. Identify the known variables and the unknown variables. So this is at 4 hours later, by the way. So 4 hours later, the original distance here, what I want to say was 150 kilometers per hour, 150 kilometers, right? I'm going to call this variable y for ship B. Okay, so this is what I'm going to call this. Now, here's the thing that you want to think about. We don't really know the position of ship A. I'm going to let this distance here be x, from here to here. This is the x variable. Okay, that's going to be an important detail. So here's x. We don't know how far it's traveled for 4 hours. We can compute that. But if this is x, I'm going to say we don't know what this distance is. What we know, though, is because the ship A is moving, it's getting closer to the line that's here. The point I'm making is that question mark value, we don't know. We can find out what that question mark is actually shrinking. So I'll let you guys know. So the question is, how do we get this question mark? Well, here's how we get it. We know 150 plus that question mark. Or I should say, we know x plus the question mark better be 150. So we're saying this distance here, which is the x variable, plus this distance over here, I'll put it green, I guess, better be the total distance 150. So we're going to represent that distance, that question mark, if we do a little bit of algebra, we're going to subtract x from both sides. So this is what I created down here as the model. I have this green distance here, 150 minus x, and maybe the gray distance here for the y variable. And they want to know, if we go back, how fast is the distance again between the two ships changing 4 hours later? So they want to know, again, over here, this distance. And that's actually going to be z. Okay, we're going to call that z here. So they want to know what dz dt will be. So this is kind of how we could get a handle on this. And notice that the variables here that are changing are x, y, and z. Those are changing. So x, y, and z are changing. They're not, there's nothing there that's being constant. So here is the geometry of the situation that we just described up here. And so from the geometry, we're going to have to figure out a related rates equation. And that's how this is beginning to work here from the geometry now. So we know again by Pythagorean theorem, it's going to be able to relate all my variables. Right? Let's go back and see 150 minus x. I don't think that was blue. This distance. And I think this was orange. Call that the y distance, and this was blue. We need a related rates equation based on these three variables that are all changing. So again, Pythagorean theorem gets applied where z squared will be, this time, 150 minus x squared. It's not x squared, plus y squared. And I want to remark here. Remember this. This is the distance for x. The x variable is increasing. Okay, that x is increasing. 150 minus x is not increasing, but x is increasing. That's a big deal. So that means dx dt will be positive. Okay, I want to also say my y variable, if I can get this in blue, y is increasing as well. So dy dt will be positive, and z is increasing. These variables are getting bigger. So dz dt should be positive. Okay, so x is increasing, but the 150 minus x is decreasing. But we're not trying to find that. We're given these rates of dx, dy, dz. Okay, we're going to have to change what that is. We called it a and b. We'll change it. But let's get the related rates equation. So I want to let you guys know when we differentiate both sides with respect to t. Z squared d dt 150 minus x squared plus y squared d dt z squared becomes, look at this as a sum. So you get 2z dz dt 2 times 150 minus x d dt 150 minus x. Don't forget the chain rule. 2y dy dt. So this is the chain portion. So this portion is going to be 150 derivative again if you want to see that detail. (150) minus d dt of x. This is going to be simply, this portion is 0, and that's minus dx dt. Okay, by chain rule. So let's write down everything that we have. 2z dz dt. 2 times 150 minus x times a negative dx dt plus 2y dy dt. And if you wanted to do a little bit of algebra, you can. Let me just rearrange some of these terms here, dy dt, and maybe put minus 2, 150 minus x, dx dt. Okay. And I guess our 2's can cancel. So we have z dz dt, y dy dt, minus 150 minus x dx dt, a related rates equation. Okay, now go back and let's figure out here. Remember, y we said this was boat A, I believe, and we'll double check, and this was supposed to be boat B. And they gave us the rate. Yes. Oh, I think I'm wrong. I have it backwards. This was B. Okay, let's be careful. This is boat B, and this is boat A. So what this means now is, let's remember, this will be dx dt is 35 kilometers per hour, and it's increasing. The y variable is also increasing, dy dt, and that's 25 kilometers per hour. So let's be careful. What was B? Go back. Yes, B was 25. B is our y variable. 25, yes. All right, so this is the information it looks like they gave us. So we can plug some things in here. Maybe we should color coordinate that. Was it orange? Yes, for y. 25 dy dt. And I believe this is green, dx dt. Okay, dx dt is 35, dy dt is 25. And they want to know what dz dt is. That's an unknown variable. Okay. So, and time is 4 hours later, so we're going to need to go back and look at some distances. We need z, we need y, we need 150 minus x. I believe it's 4 hours later. T is 4. Okay, so t is 4. So let's look at some geometry here. So let's see if we can figure some of this out here. All right, the y variable. dx dt is 35. dy dt is 25, ladies and gentlemen. And we know distances are t. So for the y variable, 25 times 4, that y variable will be 100 here. Okay. Now for the x variable, x is 35 times 4, or x will be 140. So my x is 140, but 150 minus x, just so you guys know, this is 10. Okay, so we need z now. So x is 140, 4 hours later. Y is 100. X will be 140. That difference will be 10. Y is 100. We need the z value. So by Pythagorean Theorem, we got to find z now. But remember this triangle now for z. Let me see if I can draw. It's not to scale. 10, 100, and that's the z. Distance between the two. Pythagorean theorem will say this. Z squared, 10 squared plus 100 squared. Z is plus or minus square root 10 squared plus 100 squared. Z is really the positive 10 squared plus 100 squared. Let's see what z is approximately. Let's get out the TI. Second, square root 10 squared plus 100 squared. And that's about 100.5. Okay. So this would be about 100.5. This is the square root of 10 squared plus 100 squared. Let's be careful with that. 100.5. So that's going to go down here. Okay, so I'm going to copy all this. And let's see what we get here. So we're going to have now 100.5 dz dt 100. Dy dt is orange. That's times 25. So it looks like that didn't get copied over. So we're going to put 25 and 35 here. 25, 35. Hundred times 25 minus 150 minus 140, that's 10, and that's times 35. So make sure you do the difference there. And that now means our dz dt will become 100 times 25 minus 10 times 35 over 100.5. And so let me go back because you guys didn't see that screen here. So we got the square root here of that distance, and it's 100.5. What we did was we plugged in that value for z here. Okay? We plugged in the value for z. It's 100.5. So everything else was there. Y is 100. Dy dt is 25. I'm looking at this here. Minus 150 minus 140. That's going to give you 10. And then that's times 35. So all I did was put these values here. Solve for dz dt. And you have the 100 times 25 minus 10 times 35 divided by that 100.5. And that's going to give us, solving for this dz dt that we're looking for. All right, let's try to find out what this is. Let's clear this out. 100 times 25 minus 10 times 35 divided by 100.5. And ladies and gentlemen, this is what we're going to approximate to the nearest tenths. And so this will be 21.4. I believe that's kilometers per hour. So it's a slight variation of the last example here. Okay, slight variation of it. And that's a pretty good question too. Related rates equations, ladies and gentlemen. Okay. Here's another favorite question of mine. And it says a kite is 100 feet above the ground. So just to remark, here, this is the kite. Okay, and notice it's just simply 100 feet above the ground. And is moving horizontally at a speed of 8 feet per second. And they should have, they could have put, if I had to do this again, I would use the word rate, just to get you guys used to that idea, rate. But I want you guys to know something from trig. Go back and think about trig. You have something known as a horizontal, and that's horizontal to the ground. So you have these lines here. This is like line 1, line 2. When they use that phrase horizontal, those lines are parallel, and that's important to the geometry of what we're referring to. So they're saying a kite is 100 feet above ground, and that's what makes this a right angle. Because this distance down here for that height, okay, is perpendicular to the horizontal. That represents 100 feet. At what rate is the angle between the string? So, I guess we'll say this is the string here. Okay, this is the kite. And the person down over here, there's a string flying the kite. You're generally thinking that person's like on the ground, I guess, right? At what rate is the angle between the string and the horizontal? Ladies and gentlemen, that's right in here. That's an angle. At what rate the angle between the string and the horizontal? Decreasing when 200 feet of string has been let out. Okay. So they're telling me that d dt will be negative. They're trying to ask for that particular variable, that rate, d theta dt. And when 200 feet has been left out. So in the string here is 200 feet, ladies and gentlemen. So what I'd like to say to you is a few things here. In the hint, they say, draw a picture of the question, determine the related rates equation for the geometry of the situation, and that's done really by identifying the known variables and the unknown variables. So what is known and what is unknown? Now, don't look into this, because there's a lot of things that we could look at here that we say is what is known and what is not known. What I want to say, I want to remark here in general for the geometry. You have a right triangle. And what do you know about this right triangle here? We can say a few things here. A kite is moving 100 feet above the ground horizontally at a speed. So there's a horizontal rate given. I'm going to call this x. This is what I'm looking at. Moving horizontal with a rate 8 feet per second. So this is x. And that means then dx dt equals 8. And notice that variable is increasing because it's going to the right. The kite is flying to the right in this picture. So for that variable, that's x. And then you say, what else is happening here? Well, you have a string here. Okay, so you have a string in this picture. And that is maybe h, if you want to call that h, for like the hypotenuse, of this triangle. Okay, so you have that hypotenuse. And so I want to just kind of draw a picture of what's going on. Yes, this is when h is 200 here, the string. But this is the picture that they gave me. They want to know what is d theta dt. So I'm going to have to relate d theta dt. And I need another color. Maybe I'll erase this. I have to relate these variables. They're trying to want me to get what is d theta dt. That's changing. The x is changing, and so is the h, by the way. Okay, when it's actually this particular 200 feet. So here's what I'm going to use here. We're going to use the following. Theta, 100, and x. So I want to remind people of the following here. That tangent of theta is opposite over adjacent. Tangent theta is opposite over adjacent. And then that means then cotangent theta will be x over 100, the reciprocal. And then solving for x, I get x going to be 100 cotangent of theta here. So I'm relating theta versus x. Those two variables are changing. So I'm using the definition of tangent, the fact that it's the reciprocal of cotangent, and I can solve for x. I can now create a nice related rates equation. So we have d dt of x, d dt of cotangent and theta. Now this is dx dt, derivative of cotangent is minus cosecant squared theta times d theta by chain rule. So don't ever forget chain rule. Because x is changing with time, and so is your angle theta changing with time. And let's spell that out. Let's don't put CR, let's put chain rule. So the related rates equation is what you see here. dx dt is minus, we forgot the 100. It's not a mistake if I catch it. 100 cotangent theta. So let's pull out our constant. Let's do every step. 100 ddt cotangent theta. Pull out that constant. So now let's do the calculus. 100 derivative of cotangent is minus cosecant squared theta d theta dt by chain rule minus 100 cosecant squared theta d theta dt. This is dx dt. And there you go. There's our related rates equation. So don't forget the chain portion for chain rule right here. All right, that's your related rates equation. Good. Forgot the constant there. That's an important thing. So anyway, ladies and gentlemen, let's go on further with this. You might say, okay, what do I do here? Notice what they want for us. They want d theta dt. dx dt is increasing. dx dt, they told us, was 8. So I can replace dx dt with 8. So just doing a little bit of arithmetic, I get 8 is minus 100 cosecant squared theta d theta dt. Let's just solve for d theta dt now. So we get 8 over minus 100 divided by cosecant squared theta is d theta dt. Okay, that looks good. And doing a little bit of that arithmetic, 4 goes into 8 twice, and 4 goes into 100 25 times, it looks like. And then cosecant squared, we have sine squared. And this is my d theta dt here. So I'm going to write it this way. D theta dt is minus 2 sine squared theta. Let's just write it 2 over 25. Okay, sine squared theta. But then we have to answer, what in the world is sine of theta here in this situation? What's sine theta? So go back to this triangle here. This is where the fact that there's 200 feet that has been left out. 200 feet. 200 feet of string that they're talking about in the question, right? 200 feet of string has been let out. So if I go back to this triangle here, and I have to apply a definition here, we have to know what sine of theta is. Sine of theta, here's theta, is opposite over hypotenuse. Opposite over the hypotenuse for the right triangle. That's the definition of sine. So 100 over 200 means this is 1/2. So I'm using the definition. The opposite side, okay, which is 200 divided by, 100 is the opposite side divided by the hypotenuse of 200 for that triangle, that right triangle, 90-degree triangle. 100 over 200 is 1/2. So you can say 100 over 200, sine theta will be 1/2. So sine squared theta is 1/2 squared, better known as 1/4. So I can replace this with 1/4. And sure enough, d theta dt is minus 2 over 25 times 1/4, 2 and 2. D theta dt is minus 1 over 50. Now that should make a lot of sense here. Okay? Because this is a radian measure. This needs to be in radians here. So if I go to the TI now, and I put minus 1 divided by 50, this is a numerical value. That's minus 0.02. So that d theta dt is decreasing, and this is in radians per, I guess they put this in seconds here. Radians per second, ladies and gentlemen. And, that's one of my favorite kite questions, that I look at in a related rate situation. It's radians, real number value. And okay. And then here's another situation I like because, they're talking about two sides of a triangle are 12 meters and 15 meters in length. The angle between them is increasing at a rate of 2 degrees per minute. Okay, we're going to talk about that. So they're giving us something kind of interesting here. Okay. What's happening here? How fast is the length of the third side increasing when the angle between the sides reaches 60 degrees? So there's a few things to discuss here. And yes, we want to draw a picture of the question, determine the related rates equation for the geometry of the situation. You want to identify the known variables and the unknown variables. So this is kind of simple, and let me remark about this, right? They're telling you that you have two sides here of a triangle. Now, those two sides are fixed. In this question, the sides are not increasing at all. They're constant. What is changing, what varies, is the angle theta and the distance D there, the third side. So this is that third side they're referring to. So this is kind of a nice picture of the question here. But let's write down some rates there. The only rate we have is the angle is increasing. So d theta dt. They're telling us that this angle is increasing. It's getting bigger. But they gave us the fact that d theta dt now equals, it's increasing 2 degrees per minute. Okay. 2 degrees. Remember, this has to be in radians. Pi radians over 180 degrees. So we're going to need to use the fact that d theta dt is going to be 2 pi over 180 radians, or d theta dt is pi over 90, and that's in radian measure. So we're gonna use this information here. Okay, let me do something like this. Okay. So the only thing that's changing is the angle. The sides of this triangle are constant. They're not changing. They're just having that angle increasing. And eventually the angle will get to 60 degrees. So eventually theta will be, 60 degrees eventually. Okay. They just want to know what's the related rates, or what's the rate that the distance, the third side, increasing. All right, fine. So the question is, what's the geometry of the situation? And I want people to remember something interesting about this. The reason I like this is because this is what I call a side angle side situation. You got a known side, you got an angle, and you got another side. And you have the opposite distance there. Law of cosines, ladies and gentlemen. So we're going to consider not geometry, because this is not a right triangle. This is a side angle side situation from law of cosines. And we know there that d squared will be, from law of cosines, 12 squared plus 15 squared minus 2 times 12 times 15 times cosine of the angle theta. This is just by the law of cosines for what we're looking at here. And if you wanted to do some arithmetic, that's fine. Or we could just leave it as is. We don't have to do arithmetic here. We'll just do some. How about this? I guess we'll do some. 12 squared plus 15 squared. Okay. That's 369. So this would be 369 minus 2 times 12 times 15. 2 times 12 times 15, 360. This would be minus 360 cosine theta. Remember the variables that are changing here. Theta and d. Those are the variables that are changing. Theta and d. So differentiate both sides with respect to t. And that's a theta, by the way. So, derivative of a constant. Let's use properties here. Let's do it. Properties of derivatives here. Okay. Derivative of constant, 0. Derivative of cosine is minus sine, and don't forget the chain portion, d theta dt. This is chain rule. And don't forget over here, 2d dt. And this is also by chain rule. 2d dt equals, ladies and gentlemen, minus the minus, that's plus 360 sine theta d theta dt. Divide both sides by 2, d dt 180 sine theta d theta dt. And there you go. This is your related rates equation. So then the question will become eventually, and I don't think I drew a picture here, but eventually what will happen is they want to know, hey, when the angle reaches 60 degrees, the first side was it 12 and 15? Okay. 12, 15. This is still D. Eventually, when the angle reaches 60 degrees here, they want to know what that the rate for the third side, right in here, because they gave you d theta dt. Right? They gave us d theta dt. D theta dt is right here. It's pi over 90 radians. It's a real number, pi over 90. So this portion was given pi over 90. So we know that value. And notice what we need. We don't know that d value. So you say, well, how do I get my d value? And ladies and gentlemen, again, one of my most favorite all-time courses of all time is going to be Trig Law Cosines. This labels me in a side angle side situation to find the opposite side of that angle. And again, let's just write down that word, law of cosines. So you don't always deal with right triangles, ladies and gentlemen. And that's why this is so wonderful. And 12 squared plus 15 squared, we know that's 369. And then 2 times 12 times 15, that's minus 360. And that's cosine of 60 degrees. And you guys know, just take the square root for d. 369 minus 360. Cosine 60 degrees here, so I can punch this in the TI and get this approximate distance. Take the square root. 369 minus 360 times cosine 60 degrees. Make sure your calculator is in degree mode. I know this one is. And this will be approximately 13.7 units for D. Double check we entered this correctly. Okay, I think we did. There's our D, 13.7, ladies and gentlemen. So this goes over here. 13.7. So let's see what else we can do with this. Let's see, we're ready to solve. Let's double check. Sine now of 180, or sine of 60. It's pi over, I think that's pi over 90. It just didn't come through. Let's double check. Pi over 90, yes. And theta is 60 degrees, right in here. Same theta. Okay, theta is 60, so it hits 60 degrees now. Okay. And let me just be a little bit clearer here. So we're going to punch this all in the TI. I'm going to clear this out. Parentheses. 180 times sine 60. Close that. Times pi divided by 90, okay, divided by 13.7. So double check that that's exactly what you have written down, 180. And we could have simplified, but anyway, we'll leave it as is. See what we get. Okay, let's approximate this. This is going to be 0.4. 0.4. Let's go back. iPad. 0.4 what? What was the units? Meters. And is it meters per second or meters per hour? Per minute. 0.4 meters per minute, ladies and gentlemen. And that's just a rate of change. And there you go. You know, I'm seeing this here like, you know, we could have simplified further, by the way. And double check that everything I'm doing here is correct. d dt 2 sine 60 times pi over 13.7. And we could have moved this and put just 2 pi here. Let's double check. Two pi sine 60 divided by 13.7. 0.397 again. Okay. Sorry about that. Hitting wrong buttons there. Hitting wrong buttons. There you guys go here. So that's another good example. And let's see if we should do this other. Maybe we should leave this to you guys here. Should we leave the last two for you guys? What's our time like here? Yeah. Maybe we should just leave the last two for you. Example 10. See if we can set that up. And then I like this one here too, example 11. So maybe we could either do that in another day or just leave it for you guys to do 10 and 11. So ladies and gentlemen, yeah, we're going to try that out. So we're going to leave it there for now. So you guys take care, have a great day, stay safe, and we'll see you guys later.